Very good afternoon to everybody. Welcome to this session on track with Dynamo and Revit. In this session, we'll be looking at modelling of trackside structures with products such as Autodesk Revit, Dynamo, Civil 3D, and InfraWorks, so quite a few. Before we start, let's just have some basic introductions. So my name is Lawrence Hooker. I'm a technical consultant at Excitec. I've worked with Autodesk software in the manufacturing and construction industry for over 25 years now, and been with Excitec for 18 of those years.
Good afternoon, I'm Victoria Jones. Can you hear me? Is that through? I'm a digital engineer at Lang O'Rourke. My background is precast manufacturing. I've specialised in creating data-rich family types to support the company's strategy for DFMA.
Thank you, Victoria. Okay, so let's begin by taking a look at our current rail infrastructure within the UK and some statistics around that. The railways were born in the United Kingdom and reached their peak under the Victorian rule, helping to fuel the industrialisation of Great Britain. At its peak in the early 1900s, the network was at its largest with over 23,000 miles of track. Started in the late 1950s, the beaching cuts saw the closure of many railway lines and stations, in particular branch lines and industrial hubs. This was really to try and reduce the level of expenditure that the government were providing to this huge rail industry. Ultimately, this led to over 2,300 stations being closed and the loss of over 30% of our network. Fortunately, today, all of this is now being reversed, and we're seeing the building of new high-speed rail lines and the opening of new stations at an incredible rate. So let's take a look at some of the challenges that are facing our industry. As you've just seen from the previous slide, rail usage is rapidly increasing as our roads become more and more congested. We currently have 1.7 billion passenger journeys every year, and that's expected to increase year on year by around 6%. Due to the age of the network, there are many ageing structures and assets that all need to be managed or replaced. Network Rail currently look after 30,000 structures, bridges, tunnels and viaducts, right away from the smallest bridge up to huge iconic structures like the Forth Rail Bridge. Another challenge is electrification of older railway lines. This is a major priority, and this really helps reduce pollution and noise levels along our rail corridors. Another thing is construction of new high-speed rail links, such as HS2. As many of you travelled in this morning around London, you'd have probably seen huge construction sites, really all there to support our new rail infrastructure that's going up at the minute. So Crossrail is obviously coming to completion now, but that was a huge project. The thing with this is, this all adds to a huge increase in budgets. Now, one of the things is to maintain existing assets is a huge budget. To actually build new infrastructure, which our country desperately needs, is another level of cost. The other major challenge, as you probably already know around here, is the lack of available space. So one of the things is it becomes more and more challenging to actually design new routes, new rail routes that actually meet current legislation. So there's some of the challenges, but it's not all doom and gloom. These challenges also present opportunity to help the rail industry move forwards into the future. To minimise closure and downtime, we can employ new digital design and engineering techniques that facilitate modular construction. Allow the network to capture and make better use of asset data and store this in digital 3D information models. Using these types of approaches will really help us reduce disruption and increase the capacity on the network. So there's a brief introduction to our current rail infrastructure. I'm going to now hand over to Victoria, who's going to talk about her use of Civil 3D, Revit and Dynamo on some major projects.
Thank you very much. So I'm a digital engineer on East West Rail Phase 2. And if you just bear with me. So to talk a little bit about the project, it's a large strategic project to connect East Anglia to central, southern and western England. We're going to be delivering a double-sided 100-mile-an-hour track from Bicester to Bletchley and a single-sided 90-mile-an-hour track from Aylesbury to Claydon Junction. I think it totals about 70 kilometres. So we're going to be delivering bridges, stations, highway infrastructure, as well as resurrecting the old varsity line between Oxford and Cambridge, along with some disused and mothballed sections of track. The project's going to be delivered by the Alliance, which consists of 4 companies, which are Network Rail, Volca Rail, Lang O'Rourke and Atkins. The project has a large number of BIM deliverables, of which full quantification from the model is one. So the digital engineering team, also known as the Black Arts department, were tasked with creating 3D geometry for the trackside drainage. Now, traditionally, this had been delivered in the format of schedules, 2D schedules and 2D drawings. So we had to consider a range of softwares that we could use to quickly generate the geometry because there was a very, very large number. As the task progressed, it became clear that design validation was also going to be one of the benefits of this particular exercise. We'd always assumed that the spreadsheets were correct, but as we ran the script, it became apparent that that wasn't always the case. And obviously, were we to deliver schedules to the estimators for pricing. There was also the added benefit of having the 3D geometry, which could be used for sequencing and coordination. So we assessed a range of softwares and we decided to proceed with Revit and Dynamo because we were aware of the fact that Dynamo could generate the geometry required rapidly. And also the fact that the spreadsheet we had from the designers contained all of the information required in terms of sizes and locations. So first task was to create bespoke families using Revit. So we created adaptive components for the pipes and generic models for the catch pits. And we also included in the adaptive component of the pipe family, we included a direction flow marker that was activated once it was populated with the associated parameters. So we created the Dynamo graph, which read the drainage schedule and extracted that data, converted it into lists, and pushed that into the parameters contained within the bespoke families. We were aware of the fact that this script would be used on other sections of track and probably on other projects. So we were also aware that not everybody was used to using Dynamo. So it's done in such a way that the only interaction needed by the user is to browse to the design spreadsheet, click run, and that's it, you're away. So running the graph generated the geometry to the exact location and to the correct sizes. And all of the parameters were populated with the data contained within the spreadsheet. Now, this is when it became apparent that there were actually issues with the design because the direction of flow markers were showing us that there were areas that perhaps the flow wasn't going in the right direction and that there were flat spots. It also allowed us to quickly see where there were instances where the catch pits had been, there were duplicate catch pits in the same spot. So this allowed us to go back to the design team and tell them that they needed to amend their schedule. But obviously, because the parameters have been populated, we're able to identify exactly which component it was that had got the issues. One of the reasons as well that we chose Revit was its fantastic scheduling features. We could create schedules within the software to perform additional calculations, which we collaborated with the estimating team to just figure out how they manipulated their designer spreadsheets to extract the data that they wanted. And we built the schedules as standard within the Revit template so that whenever we ran this script, it automatically calculated whether there was adequate cover, the pipe banding, the pipe lengths, which proved really useful. We created an additional Dynamo graph. Revit does have a tag all feature, so once we'd created the geometry, run the script, generated all of the geometry, obviously we had to tag everything up, but using the Revit tag all feature would have still meant that we would have had to have gone in and made some amendments because we needed to identify different parameters for catch pits and pipes. So we quickly put together, and it did not take long at all, a quick script that tagged everything as we needed. So what we would do is go through and create all of the layouts, all the sections, and then run this script to tag everything, and then just place that on the 2D drawing view, and it's ready to go with barely any interaction. So it was considered a success. The amount of time that it saved being able to generate this geometry was it was unreal. To actually place all of those components, set the size parameters, populate it with the data, it would have taken a significant amount of time. So this exercise saved quite a lot of time. It also allowed us to issue a full set of drawings and schedules to be issued for pricing, and we had graph and standard template for future projects. So following on from the drainage success, there was an exercise that came about for the pipe trenches. So where we had a 3D model of the drainage, which we don't ordinarily have, we realised that we could do another exercise where we could actually use Dynamo to identify the location of this geometry and fire off points around it to generate the levels to calculate the pipe trench volumes. We also used Dynamo to bring in a topo surface and do the conversion, and we created an adaptive component family that had a huge number of adaptive components that flew up on the z-axis and terminated at that topo surface. So it gave us a very, very accurate volume. We're also writing another graph at the moment to place culverts and headwalls, and it's a very, very similar process to the trackside drainage. The main difference is that we're populating quite a lot of the parameters with text information in relation to the works, as opposed to just dimensions and levels. There's also the opportunity to populate models that we perhaps receive that are lacking in data. So we do receive those where there's so much information missing, and we can use Dynamo to rapidly push information back into the model. I'll hand you back to Lawrence.
Thank you very much, Victoria. Thank you. Okay, so what we're going to do now is spend a little bit of time looking at the modelling of trackside structure. In this particular case, it's going to be a platform extension that you can see in front of you here. So what we're going to do here, we're going to actually look at first how we position the cross walls that you can see here. Now, all of this system is a precast system, and we've used the Dynamo script here to actually place out these precast members. These have been modelled in Revit as beams, so they have analytical models. And of course, with a beam, it can be placed down by a line rather than 2 points. So we're actually out there letting Dynamo place these across lines. So the next step is to place the precast hollow core planks. These are variable. You can see we've got two different widths here. That really is dependent on how wide we want the platform, but this is modular, so of course it can accommodate all sorts of different widths. Again, they're beam members. And finally, what we're doing is we're placing the precast coping stones along the edge of the platform here, and also creating a structural topping over the top of those precast planks, which would be an enormous task to try and do inside Revit alone. But of course, it's not all just about pretty 3D models. What we're looking at here is the generation of proper drawings as well. So you can see on the left-hand side here, we have a cross-section. If you look on the right-hand side window, you'll see that we've got grids here. The grids are derived directly from Civil 3D. I'll show you how to do that very shortly using Dynamo. And what we're then doing is we're cutting sections automatically through every single grid, and that's the output of those sections here. Notice on the rail alignment as well, we have cant on the railway, and of course that's going to have a knock-on effect to the position of the precast coping stones on the side of the platform. So again, Dynamo's taking care of all of this for us. So, what you'll notice here is throughout this workflow that I'm going to show you, we are using a lot of Autodesk products. So you can see here that we've got Revit, InfraWorks, ReCap Pro, Civil 3D, Dynamo, and Navisworks. What we're doing is we're just using certain pieces of each bit of software to get the process as automated and as efficient as possible. And what this does is it really does highlight the power of the AEC collection. So what we can do is use all the tools in the collection to actually leverage the most power out of it. And that's really what we're doing throughout this presentation here. So the next thing we have to understand is the workflow. If we're doing a precast platform, is it a new structure or is it an existing structure? If it's an existing structure, we'd probably laser scan that, and then we'd take that laser scan into ReCap Pro, prepare it, and go on from there. Or it might be that we've already got a Civil 3D alignment and corridor, and we simply want to go into detailed design for that scheme. Now let's look at these workflows in a lot more detail. So if it's an as-built structure, clearly we're going to be starting off with a laser scan. So we can take that into recap, we can then process the laser scan, we can index the scan here, and we can then just slice out the area of corridor that we're interested in. We're then taking that into InfraWorks. The reason why we're using InfraWorks here is we're actually using linear feature extraction, which is going to extract out the rail lines, yeah, and we can then utilise those in Civil 3D to actually make an alignment or a corridor. We then output a corridor points report from Civil 3D. That's output as an Excel file. Dynamo reads that Excel file and then models the entire platform from that Excel sheet. Now, it sounds like a fair old workflow, but the interesting thing with this is, if I go back and actually change the Civil 3D alignment, Revit will update all of the components in the platform because it's linked to the spreadsheet. Now, of course, as an as-built workflow, you wouldn't really want to do that, but if it was a new structure, then of course you would. So you can see for new structures, the workflow is almost identical, but of course we just drop out the reality capture part because there's no existing structure. And here we have an existing scheme, and this will be if we already had the alignment and corridor created in Civil 3D, and we're just going to use Revit and Dynamo to go into detailed design. Okay, so let's have a look at some of these processes in a bit more depth. So this is the reality capture in recap. And what we're seeing here is the laser scan, obviously in recap, all the points have been indexed, and currently we're presenting this with point intensity. And the idea with that is you can clearly see the rail lines have shown up in a much higher intensity. I can then move forward and then start to isolate that rail corridor. So you'll now notice in the rail corridor here, we have just the strip isolated there. That's a really important step because when you look at the next part of the workflow, which is in Autodesk InfraWorks, what we're going to do is we're going to actually use point cloud terrain marked up with point number 1 there. Now what this does is it will actually model a very accurate surface over that point cloud. Now of course if you try and do that for a very large area you'll be sitting there waiting for a long time, so you must optimise that corridor in recap first. What you then do is you go on to point number 2, which is your linear feature extraction. Now if we have a look at how that actually then works, first thing we do is we go ahead and choose a style. So in this case I've used the rail style there. And then we can simply pick 2 points and it then generates the path. Now to show you that in action, I've got a quick video you'll be able to see here. So there's the modelling recap. We'll go into the linear feature extraction tool up here. We can then pick 2 points. Obviously here I'm choosing my style. That's a custom style that I've created there. Now we'll just select 2 points. The distance between those points will control the accuracy. This is actually quite a low density point cloud, so it's not that accurate anyway, but it's just really showing you the concept. And then you can see here that InfraWorks is extracting the existing alignments out of those rails there. The real neat part, once you've done that, is you can select that and go into the Crosssection Editor. Now what this does is you can see here that it's actually superimposing my linear feature extraction elements on there over the point cloud. So I can then manually start to adjust those and get it absolutely perfect, yeah, using the cross-section editor there, which is quite good. Okay, so moving on a bit further. In a minute we're going to do a live demonstration, but before I do that I just want to make you aware of adaptive components because absolutely everything on the platform, other than the cross walls, are all done with adaptive components. Victoria also mentioned a little bit about adaptive components. The reason why we're using these is they can control rotation by picking 2 points. So I haven't got to start to worry about getting Dynamo to calculate angles and so on. So that's why we're using adaptive components there. Okay, so we're now going to move into a live demonstration. So just switch the screen over. Okay. Now, what I've got running here is Civil 3D, and in Civil 3D here, you can see that we have currently the corridor over here. This is the cross-section editor, and as I start to step through these sections up over here, you can see that on the straight part of the railway there's no cant, and as I start to go through into the curve, you can then start to see the cant forming in there. In this viewport here, I've simply got my vertical profile designed in there. And over here, I have a sub-assembly that I've created. Now, Autodesk actually deliver a standard sub-assembly you can use, but I've actually edited this one in order to get point codes out. Okay, and the point codes are really quite important. Let's have a think about point codes. If I go to the Toolbox tab here, you'll notice that I've got something called a corridor points report here. If I right mouse over that and execute this, what I'm going to do here is pick on the corridor that I'm interested in, and you'll notice here that I have centre line of rail. Yeah. Now, what I can do, if I pick on that, that's actually going to extract out all the centre lines from those 4 railway lines. What will then happen is we'll get this corridor points report out of it. Now, if we just study the corridor points report for a minute, you'll notice that we have in the US what's termed as a station, but what we'd term in the UK as a chainage over here. We have an offset, a northing, an easting, a level or an elevation, and the point description. Now, the point description is the important bit. That's what I've added in to my sub-assembly. Yeah. Now, for the platform, all I'm really interested in is the centre line of rail A. Okay. So now, what we're going to do is shift into Revit and Dynamo. Now, before I actually set myself loose on Dynamo, which I may live to regret in a minute, we'll see. What we have here is a project base point, okay? If I click on the project base point, that is coordinated. So what I've done is I've actually used that project base point as my local datum in Revit, okay? If I just quickly switch back into Civil 3D, in Civil 3D, some of you may have noticed the big green circle that I've drawn in there. That corresponds to that local datum, okay? So what I'm actually doing is I'm then producing corridor solids from the corridor here, outputting those as DWGs, and then importing those into a family file using that common datum. So that allows me to get a fully coordinated model into Revit. So what we'll now do is we'll start to have a look at the whole thing with Dynamo here. So, first thing I'm going to do is create a new graph. And what I want to do is access the Excel spreadsheet. Yeah? So I want to read from file first. And you can see here that the inputs we're going to require are the file, the sheet name through here, and read a string, which is a Boolean. So let's go and get the file out here. So what this is going to do is read the file from the path, and then what I can do is I can just browse to the file, yeah, in here. So if we do browse in there, yeah. I can now go and grab the file from here. So let's go and get that, the file path. We'll browse. We'll pick on our Excel file, and I'll connect these together. So that's now reading the file, and that's passed that into Excel read from file. What I now want to do is get the sheet name out. So here's the sheet name, Civil Report. You'll notice that I've kept the report native. So if I update it in Civil 3D, I don't have to do any pre-formatting. Yeah, that's the best way to handle this. So we'll go back into Dynamo now. And I'm going to just use a code block there to paste that in. So let's paste that in there. And that goes into sheet name. And read a string. I don't want it to read the strings, so I'm going to type in false there. So that's a Boolean switch. It's either true or false. And now, out the back of this, you'll see that we've now got the data from the Excel spreadsheet. Yeah. Now, what you will notice, if I just switch back into Excel, can you see that the data doesn't really start to make any sense until it gets to row 15? Yeah. So what I want to do is drop all of the earlier data in there. So we can use drop items. Okay, we'll bring that node out, we'll bring the list in, and the amount of data that I want to drop is 14 parts. So now, what I've actually got is the raw data that's required. Just before we move on, how many of you guys have used Dynamo? Let's just see a show of hands quickly. That's brilliant. A lot of people. Fantastic. So most of you Dynamo users will know all about lists and nested lists, and you can see here I have a nested list. And what I'm actually interested in here is harvesting everything that has, on index 5, the centre line of rail A. So what I'm going to do here is I'm going to start to group my lists. Yeah? So I'm going to use a group by function over here. So I'm going to pass the list in. The function I'm actually interested in here is get item at index. So we'll bring that out. And the index I'm interested in is index number 5. Okay. Now, if we just start to clap some of these sublists in here, you will now notice that I have 4 sublists there, for 4 tracks. The one I'm actually interested in is sublist 0, and you'll notice that each index on sub-index 5 there is for centre line of rail A. So what we need to do is just isolate that. So I'm going to use a bit of design script to show you how to do this. So you know we can use list get item at index. In this example here, I'm just going to put in something like this. Okay, and what that now does, that's a way of saying get item at index. That's using design script. So I'm declaring a variable x, and I'm getting everything at index 0. Right, we now need to isolate the easting, the northing, and the level. Yeah. So I'm going to use get item at index again. Over here, we'll pass that list in, and you'll notice the easting is held under index 3. So let's pass that in there. But when I do this, can you see I only get one list there? That's because I need to go down to the next level. One of the great things with Dynamo is I can just say use levels. And you'll now notice that it's getting all of those easting values out. So now we can just use some good old copy and paste in here. So we want to now get items at index 2 and paste again items at index 4, which will be my levels. Now, of course, Civil 3D works in meters. I'm working in millimeters in Revit. So we now need to start to do some transformations in here. So what we're going to do is take the values and we're going to multiply them by 1,000. Okay, so we'll just pull those through here. I'm copying there just by holding the control key down and dragging those nodes. That's the quickest way to do it. And what we now have, of course, is the values in millimeters rather than meters. Now here's the next bit. I want to make sure that these are being placed in the right context inside Revit. So what I have here is a project base point already set up. Yeah? And these values across here are actually in correct coordinates. I want to deduct the project base point from these values here. So what I need to do is make sure I can actually get the project base point. So let's use Dynamo to do that. So I'll go ahead and find categories in here. What we're interested in is the project base point through there. Here I'm going to get all elements of category out through there. And now what I want to do is get the values of certain parameters. Now this is a very powerful Dynamo node. I'm sure most of you have used this in the past. And what we can do is put the elements into here. The parameter name I'm interested in is east-west. Whoops, east-west over there. And can you now see that it's fished out the easting from there? Yeah. Now let's move that out the way a little bit. I need to do exactly the same in here for the north-south. Yep, so we'll do north-south in here. And there we have it. What we now need to do is deduct that from these values here. Yeah? So let's make another code block. And we'll put in chords minus SOP. Yeah? Bear in mind, when I declare these variables, they could be anything. I'm just using my own variables here. So what I'm going to do first is put in the coordinates into here. The setting out points are these over here. Now, here's an interesting one. Can you see I've only got one value out from there? In normal Dynamo nodes here, we have something called lacing, where you can say shortest, longest, or cross product. Here I haven't got that. So what I need to do is actually use some design script to allow me to pull that information out in a slightly better way. And now you can see that I've got lacing going on through there, which is quite clever. So just remember those little chevrons, neat little trick, that one. What I also want to do is flatten the list here. Yeah. So I could obviously use a node for flatten, but I'm just going to use some design script again in here, like so. And can you now see it's flattened that list down? So there's my blueprint for the other set of coordinates. So they can go in there. My setting out point is now this one over here. There they are. And of course, can you see that we've got negative coordinates in there? That's obviously going to happen because we're going to the left of our project base point. Yeah, that's fine. What we're then going to do is now plot some points on this. So we'll do point by coordinates over here, and I can now take the X, the Y, and the Z in. Already in the background of Dynamo, you can start to see points forming. Yeah. If you remember the curvature on the railway, there it is. Let's put the Z in now as well. But as soon as I do all of this, you'll see that actually these nodes have gone yellow. The reason for that is we've gone outside of the working range of Dynamo. It has like a geometry range that we need to set. Generally, if you're working with buildings, it's not really a problem. Working with railways, obviously, they're a little bit bigger. So what we need to do here is go to geometry working range. And in this case, I could choose large or maybe extra large. And you can see that then purges the problem. OK, and you can now see that we have all of our points out through there. The next thing we'd need to do is actually go ahead and draw a spline through that. So we can just go to NURBS by control points in here. And you can now see we've drawn a spline. Now let's look at that inside Revit, because this is quite important, because obviously the entire platform extension routine is all driven by the rail alignment. So if I change the rail alignment, everything else updates. And you'll now notice that we've got perfectly that track center, yeah, on there. If I go into another view, perhaps this perspective view here, again, you can now see that track center running directly through that left-hand rail track there. Okay, let me just see how I'm doing for time, because I do tend to ramble when I get going with Dynamo. Let me just see where I am. Yep, it's all looking good. Okay, so what I'm going to do is I'm going to now open up a more complete Dynamo script, and I'll run it so you can see how it operates. And I'll talk you through the remainder of the script. Okay, so let me just close this one down. Okay, and what we'll do is we'll go ahead and open up this one in here. There's the finished script. Now, actually, I got up to this point here where I created those points, right? So then what we've done is we've taken the points out, we've created the NURBS curve. Now, here's where the clever stuff starts to happen, actually, because what I want to do is I want to actually divide that curve up into points and offset it. Now, if any of you have tried to offset a three-dimensional curve in Dynamo, it's very, very difficult. You can't really do it because it's changing through three-dimensional space. So what I'm doing here is as follows. You can see that I'm putting the curve onto a flat plane. So notice there we've got the plane XY, that's a flat plane. I'm projecting that curve onto the flat plane and then offsetting to get the offset to the platform coping stones, the edge of the platform over here. Of course, I don't want to end up with a flat 2D curve. So what I'm then doing is I'm taking the original Z coordinates, breaking down that curve into the XY points, and then adding the original Z component back in, which gives me that perfect three-dimensional curve for my platform edge. We then have to do some splitting of points here. So I'm actually taking that curve and splitting it down by points in here. I'm then getting the start point and the end point of each curve. That gives me the two coordinates to go ahead and place my adaptive components down. So here's the part where we place the adaptive component. If we go ahead and run this now, it will just take a few seconds to place these stones out. Obviously, we can change the family type over here to whatever we want. So let's just let this run through. Okay, if we go into Revit now, we have some coping stones through there. Now, what's quite clever with this, if I select one of the coping stones, remember we said it's not all about 3D models. If we have a look on the left-hand side in the properties palette, I've got the easting, the northing, and the level for the start point of my coping stone and for the end point of my coping stone. So I can set that out on site very easily. I have Dynamo generating unique references for each stone. So that one's a CP121. If I go to its next door neighbour, that's the 122. If I go into a pre-formatted schedule, you can see that it's now pulled out all of that information directly into this schedule for me. And of course, if I go down to the total weights and quantities here, you can see that I'm now getting the total weight of all those coping stones out. Now, in actual fact, we can go right the way down to barcoding these things as well when they turn up onto site. So if we're getting prefabricated sections made, we can get Dynamo to generate barcodes, if we want to, or QR codes, yeah, that we can then identify out on site. Okay, so that's the basic workflow for those coping stones, but that same workflow can be actually used for everything. So if you have a look at one of my cross walls over here, you'll notice the cross wall is actually a beam, so here it's structural framing. Notice that that's always vertical, but of course these ones are raking because the platform's on an incline and also on a curve. So actually setting out all of this without Dynamo would have been very, very manual, and it would have taken a long, long time, especially when the alignment engineer comes back and changes the alignment of the track. Okay, so moving on from that, if we go back into Civil 3D here, one of the most important things for this is to make sure that you get the corridor out and the corridor solids out first. So what I'm going to do is just go ahead and select the corridor in here. Not sure if you're aware of this, but in Civil 3D, you can extract those corridor solids out as physical solid bodies. And like I say, when I actually do this, Civil 3D will take out all of the solids, as you can see here. So there's one solid. If I just list that, you can see that's a 3D solid. When we extract that out, not only are we taking out the solids, but we're taking out that green circle, which gives me that datum, that local datum inside Revit. Another very important part of the workflow, if we just minimize Dynamo for a minute, let's select, for example, the ballast over here. Now what I've done is I've actually pinned these structures, and I've told Revit not to select the pinned elements, just so I don't constantly keep selecting the wrong things in here. Let's do that. So, whoops, let me just be able to select that element. There we are. So if I pick that, I'm going to edit the family. Notice in the family editor here, we have the original datum circle that I pulled out from Civil 3D, along with the corridor solid. Now, when I pull the corridor solid out, what you notice is when it'll just be one big lump. That's no good because Revit won't section that. So what you have to do is a partial explode on that. Then it will explode that back into Revit geometry. And what I've done here is assign my own subcategory to that so I can control how it visually looks inside Revit. So let's go back into the main project. And in here, if I go to Visibility Graphics and I open up my generic models in here, you'll notice that I have one for the ballast. So if I uncheck ballast, obviously that ballast disappears. If I do the same for my overhead line equipment in there, platform coping stones that we've just placed out with Dynamo, yeah, we can actually control all of those various different elements, not only how they appear in a plot or a print, but also how they would appear on the screen. Now, for those of you who are thinking of IFC formats, you can also use the subcategories there to correctly export these out as IFC, so you can classify those parts in an IFC file. Okay, so that really concludes the demonstration part, and we'll just switch back to the PowerPoint, if we may. Good, I didn't break anything, which was fantastic. And really, that's the end of what I wanted to show you here. So thank you very, very much for your time. We are going to have some time for questions, and I'm sure some of you will have some questions that you might want to ask. I think somewhere here we have a microphone that we can pass around. Any questions for anyone? So we'll just pass the microphone across. Thank you very much.
Hi, thank you. So I saw that you are using a lot of custom nodes. Were you forced, let's say like that, to use Python at any point?
No, no. So everything in my presentation is using standard Dynamo nodes. I haven't used any custom nodes at all. There are instances where you might need to use Python, but generally, as a general rule for myself, if I do use custom nodes, I tend to depackage them. Because the problem is, if you share the Dynamo script with someone else that hasn't got the package, it causes havoc.
Yeah.
Quite right, yeah.
Thank you.
Thank you. Any other?
Yeah, hi. I noticed that this workflows were civil to Dynamo to then Revit. But if you all use, I know back in Sweden they use a macro station to generate the tracks and something like that. Could it work if we replace like civil with macro station and generate the alignments lines and go on to detail the details in Revit and Dynamo?
That's a fantastic point, and that's very relevant in the UK as well. We'll find that most people do use Bentley tools to create alignments, but what we can do is we can take that alignment into Civil 3D via a Genio file, and then we can continue with our workflow. So we still use Civil 3D to copy the alignment from the MicroStation product, but then we use our corridor points report to start the process off. So yes.
Yeah, in the workflows that you showed, you mentioned Dynamo Studio. Is it Dynamo Studio or Dynamo?
Right, I've just used Dynamo, but you could equally use Dynamo Studio as well. There's no additional Dynamo Studio functionality that I've used in this workflow, but for the sake of putting the product up on the slide, there's an icon for Dynamo Studio, which is why I used it, yeah. And it's also part of your AEC collection.
Do you use the model to set out the platform, or do you use the geometry given to you by Atkins to set out the platform?
Well, this particular example here wasn't an Atkins example,
Right.
but the ruling factor for the setting out of the platform is that alignment data from either Civil 3D or an outside source. So, but that is the key to the setting out of the platform.
So you're using the design to set out the platform,
that's right. We're using the alignment, and the corridor, Thank you.
Did you experience problems with the limitation of the range in Revit? Do you know there is the 20 kilometers radius?
There is a 20-mile or a 33-kilometre bounding box that goes around Revit. Bear in mind with this type of procedure here, we're really only dealing with smaller areas. We're never really dealing with a 20-mile stretch of track. We're dealing with structures that go alongside the rail track, like like the platforms or potentially like bridges, tunnels, that sort of thing. But I think that the key takeaway for this is that everything we do is based on that rail alignment. And the problem is, if we spend a lot of time modelling the structure and then the alignment changes, we have problems. So using this approach here gives us complete design automation. Yep. Okay. Right, well, that concludes our presentation. We're a little bit early, but it's all good. We can stop for a nice early cup of tea or a very cold drink. So thank you very, very much. It's been a pleasure talking to you. Thank you.